Ampere's law. Ampere's law is based on the work done by Andre and Marie Ampere. The amp, of course, is named after him. He's credited with discovering electromagnetism, or the relationship that you can generate a magnetic field from electricity and vice versa. In any case, Ampere's law is very similar to Gauss's law. In Gauss's law, we looked at the flux passing through an area and set that equal to the amount of charge contained within the surface that surrounded that, and of course multiplied or divided by a constant. Ampere's law is very, very similar in that respect. But instead of taking a surface and wrapping around a charge with that surface, we're going to take a loop and we're going to wrap a loop around current. And in this particular case, we're not calculating flux, but rather we're integrating the magnetic field along some imaginary line to obtain the strength of the magnetic field. By Ampere's law, the integral of B dot dl is equal to the constant mu0 times I, the current which is enclosed by this loop. Okay, so how does it work? Well, like Gauss's law, it's somewhat limited. You have to have the symmetry of the loop match what is carrying the current. So for instance, if you just have a random loop going around a current, that magnetic field is going to vary based on the radius. We've already seen that earlier. So again, we want to match our symmetry of the loop to the wire. In this case, if we have an isometrical loop around the wire, then Ampere's law is going to work because the magnetic field will be constant. We can solve that particular problem. So again, here's Ampere's law. We imagine we have current. In this case, the current is coming out around us. We surround it with a symmetrical loop, or in this case, a circle. Okay? Everything has a constant distance, a constant radius from the current. Again, the current's coming out right here. By Ampere's law, it states that the integral of B dot dl, dl represents an infinitesimal length along this particular path that we have, is going to be equal to mu I. In this case, if we integrate this, the magnetic field is constant. We can take it out of this. We can integrate along the length of this wire. And of course, if we have a circle, what's the path around a circle? It's a circumference. It's 2 pi r. So B times 2 pi r, this is what was left within the integral, is equal to mu0 times I. So we get the same result that we got before when we used the Biot-Savart law. However, the amount of steps that it took is much, much less. Here's Ampere's law. Here's converting Ampere's law with the using the symmetry that we have. Here's the result. Not that much math going on right here. So again, we get the same result that we got before. It's very useful in terms of symmetries like a straight wire, where we can easily match the symmetry of the loop to the current that we have. But again, we're limited. More complex shapes, it's not going to work, just as Gauss's law didn't work for all the distributions of charge. Here's an interesting case. Let's do Ampere's law for a wire, but we're going to go inside the wire this time instead of looking at the magnetic field further away from the wire. Again, we have this integral. We're integrating B dot dl equals mu0 times I. For the outside of the wire, we already did that, so we got that result. That was a previous result. But now inside the wire, it's a little bit different. By Ampere's law, we only include the current that our circular path is going to enclose. So if you look inside the wire itself, the radius that we look at is going to be less than the radius of the wire inside the wire. So now, again, here's Ampere's law, except for I, is going to depend on, how close to the center we are. I is equal to the total current, I0, times A, the fractional area that we've enclosed, divided by the total area, A0. So converting this right here, I0 being the total current going through the wire, we have the fractional area, pi divided by pi cancels out, and now the total current that the current that we enclose is equal to a fraction of the total current, where R squared represents the distance from the center, and A squared represents the radius of the wire itself. So, reinserting this back into our original, we get that the magnetic field is equal to mu 0 times I0. I0 again is the total current, divided by 2 pi R squared over A. R squared divided by R becomes R, and this becomes our new expression. Interesting that the magnetic field actually depends on the distance from the center. And if R is 0, if we're at the center of this wire, the magnetic field is actually 0. So if we graph the magnetic field as a function of radius, the magnetic field drops to 0 at the center, gets larger and larger, assuming that the current is constant, and right at the surface, that's where the magnetic field is the greatest. So an interesting and unexpected result from Ampere's law, because you'd almost expect that the magnetic field would be fairly constant inside the wire. It's not.